Question 52, LeetCode n queens 2. The n queens puzzle is the problem of placing n queens on an n by n chessboard such that no two queens attack each other. Given an integer n, return the number of distinct solutions to the n queens puzzle. So we need to return the count of positions of the board where no queens are attacking each other. Now a queen's attacking capability is across the row, across the columns, up and down, left and right, and diagonals. So here, as you can see in this one, none of the queens are attacking each other, and the same with this one, which is a mirror image. With this solution, it's almost identical to n queens 1. What we need to do is we need to create some helper functions to check the validity of the position. What we need to have is valid function. We already know that we're going to be going across the rows. We're going to allocate a queen to each row because we know two queens on the same row is not a valid option. We need to check the columns. We need to check positive diagonals and negative diagonals. And how we work that out? With positive diagonals, say a queen is here, we have position 3, 0, 2, 1, 1, 2, and 0, 3. To keep these positions constant, we need to add row and column. So 3 plus 0 is 3, 2 plus 1 is 3, 1 plus 2 is 3, and so on and so forth. So that is how we calculate the positive diagonal. In order to calculate the negative diagonal, queen is coming in here. We have position 0, 0, 1, 1, 2, 2, 3, 3. We want to keep all of these constant, and we can't add them together because that will give different values for each. So we subtract them. So it'll be row minus column. 0 minus 0 is 0, 1 minus 1 is 0, 2 minus 2 is 0, and that should be 3 minus 3. So that's how we calculate the negative diagonal as well. Okay, so with this information, we can check if the board is valid. We need a variable count, which starts at 0. So we can count how many boards we can create where the queens aren't attacking each other, and then we just carry out the recursive backtracking solution. So we position Q1 here first. There are no other attacking boards, so Q1 has n options to choose from at this position. Q2 cannot go here, because this Q, or this queen, is attacking these positions. So Q2 needs to go here. So Q2 has only n minus 2 options. Then we move on to the next row. So looping through the rows, check if Q3 can go in this position. No, it can't. Can it go in this position? No, it can't. It's been attacked here. Can it go in this position? Nope. This position? Nope. So we need to backtrack at this stage. So we go back to Q2. We remove Q2 from this position. So we clean up and we move Q2 along. So check if it can go here. It can go here because it's not being attacked. And then repeat this process. So Q3, can it go here? Nope. Can it go here? Q3 can go here. Now we go to Q4. Can Q4 go here? No. Here? No. Yep. No. Yep. No. So we backtrack. We remove Q3 from here. Check to see whether it can go in the next position. No, it can't because it's being attacked from here. Can it go here? No, it's being attacked from here. So we have to move back and backtrack again. So we clean up Q2, we try and move along. We're out of range now. So we go to Q1 and we move Q1 along. So Q1 moves to here, go on to Q2. Can Q2 go here? Nope. Here, no, here, no, here, yes. Q2 goes here. Now on to Q3. Q3 checked in the first position, it can go there. So we move on to the next position, Q4. Q4 can't go here, it can't go here, but it can go here. Now we know we're in the last row, so we can increment count. So count becomes 1. So now at this stage, we just backtrack and check all other possible solutions, and the final count is going to be 2. So what's going to happen is we're going to backtrack, we're going to check the other position. Q4 can't go anywhere else. Q3 can't go anywhere else. Q2 is out of bounds on the next move. Q1 moves along. Q2 can go here. Q3 can't go here, here, here. So Q3 goes here. Q4 can't go here, but it can go here. So that's the second count. So we know because we're at the last row, we can increment the count. So time and space complexity. Time complexity is O(n) factorial, where n is the number of queens. And the reason for this is because here we have n options that Q1 can choose from. So it can go here, 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 or here. With Q2, Q2 is going to be attacked by down and right. So it's n minus 2. So it can go here and here. So we have n options, n minus 2. So that signals n factorial. Okay, so let's write this out. So we have columns, which are going to be a new set. We have positive diagonals, which is going to be a new set, and negative diagonals. We need to have a count variable. And now we need to create helper functions. So as we stated, we're going to have an isValid function. This is going to take in row and column, and it's going to check to see whether the column has an attacking queen, whether the post diagonal has an attacking queen, or whether the negative diagonal has an attacking queen. And here is where we're going to use the set. So if column has C or pos diag has R plus C, neg diag has R minus C. So that's the first helper function. We also need a helper function for adding the queen to its position. So add in the values within the column, the positive diagonal and the negative diagonal. So we take in R and C. We add into the column set, positive diagonal set, and the neg diagonal set. And the last helper function will be to remove the queen. So the cleanup, which we're going to need for this backtracking recursive call. So with sets, there is the delete method. But now we can create the backtracking function. So let's call this function recurse. We're going to be recursing through the rows. So we'll call it row and say we return recurse starting with 0 row. In here we need a base case for the recursive call. So when it ends, so if row is equal to n, then we can increment count. Now we need to loop through the columns. Call needs to be less than n, and now we need to use our helper functions to work out this solution. So check if it's valid at this position. So if there are no attacking queens, then we can simply add the queen, use that helper function, pass in row and col. We can recurse. So here we need to specify that count is equal to the recurse function being called with row plus 1 because we want the next row to check for potential solutions in the next row, and we need to pass in the count as well. And finally, we need to backtrack. So if the solution isn't optimal or we can't find a solution without attacking queens, we need to clean up. To do that, we do remove queen function with row and col being passed in. And finally, we need to return count. Let's check to see if that works. Okay, it's been accepted. Let's submit it. Okay, and there you have it.